Welcome to Lesson 1.4 Neural Networks at a Glance. Neural networks are the backbone of modern artificial intelligence, powering breakthroughs in computer vision, speech recognition, and natural language processing. In this lesson, we'll walk through the core building blocks of a neural network, explore how learning actually happens, compare shallow and deep designs, and uncover why stacking layers gives these models their incredible power. By the end, you'll have a clear picture of what makes neural networks so effective. So, what is a neural network? A neural network is built from simple units called artificial neurons, arranged into layers. The input layer receives the raw data, for example, pixels in an image or words in a sentence. Hidden layers sit in the middle, transforming inputs step by step, while the output layer produces a final prediction or classification. Connections between neurons are weighted, meaning each connection has a strength that can increase or decrease the signal. These weights are adjusted during training. To allow networks to capture nonlinear patterns, neurons apply activation functions such as sigmoid, ReLU, or Tana. Without these, networks would only model straight line relationships. Together, layers, weights, and activations create a flexible system capable of learning high complex mappings from input to output, the essence of artificial intelligence. Training a neural network follows a cycle made up of two main phases: the forward pass and the backward pass. In the forward pass, data flows through the network from the input layer to the output layer. The network produces a prediction, which is then compared to the correct answer using a loss function. This tells us how far off the prediction is, the error. In the backward pass, also called backpropagation, that error is sent backward through the network. Each connection weight is evaluated to see how much it contributed to the error. Using an optimization method such as gradient descent, the weights are then adjusted slightly to reduce the error. This forward and backward cycle repeats thousands of times. With each iteration, the network learns a little more, gradually improving its predictions until it can recognize patterns with high accuracy. Neural networks can be categorized as shallow or deep. Shallow networks typically have one or two hidden layers. They are easier to train, faster, and require less computational power. However, their representational capacity is limited, making them suitable for relatively simple tasks such as basic pattern recognition or linear classification. Deep networks, on the other hand, include many hidden layers, sometimes dozens or more. This depth allows them to build hierarchical representations. Early layers detect simple features like edges, middle level layers combine these into shapes, and later layers recognize complete objects or concepts. The trade off is significant. Deep networks require large data sets, powerful hardware, and longer training times. Still, they enable breakthroughs in fields like image recognition, speech processing, and natural language understanding. Capabilities that shallow models cannot match. One of the most important insights about neural networks is the representational power of layers. Each layer in the network transforms its inputs into a new representation. For instance, converting raw pixels into edges or edges into shapes. By stacking multiple layers, the network can progressively build more abstract features. This allows it to represent complex, nonlinear relationships that would be impossible to capture with a single transformation. In mathematical terms, deeper networks can approximate more complicated decision boundaries, making them suitable for tasks like language translation or medical image analysis. In essence, depth gives the network expressive power, the ability to represent and learn patterns of almost any complexity, provided sufficient data and training resources are available. We see neural networks at work all around us. In image recognition, shallow layers detect edges, and deeper layers detect shapes, and the deepest layers recognize objects like cars or faces. In speech recognition, early layers analyze sound frequencies, middle layers group them into phonemes, and later layers combine phonemes into words. Pardon me. Recommendation systems, such as those on streaming platforms, analyze past user activity, and early representations capture raw viewing or purchase history, while deeper representations uncover latent factors such as genre preferences or hidden similarities between products. These examples highlight how neural networks transform raw data into progressively more meaningful representations, enabling them to power everyday technologies we now take for granted. All right, in this lesson, we walked through the core building blocks of a neural network. We were able to explore how learning actually happens. We compared shallow and deep designs, and we uncovered why stacking layers gives these models their incredible power. So now, take a moment to review your notes, and when you're ready, we'll move forward to the next section and continue building your expertise.